Hi, my name is Aishwarya C. Warrior, and I will be explaining to you today a comparative study of zero forcing equalizers and minimum square error equalizers with MIMO systems. My presentation contains an introduction to MIMO and also a brief description of equalizers that are ZF equalizers and MMSE equalizers. I will also be explaining about successive interference cancellation when used with the above mentioned equalizers. I will proceed to explain the problem specification with respect to my report and also discuss the MATLAB code and give a final analysis. As we know that nowadays mobile multimedia and internet application have increased to a great amount. People are constantly streaming videos and downloading things which are of high memory. This has led to the high demand of throughput, coverage and reliability. This high demand most of the time is not being able to be met up because of the challenges like bandwidth limitations, transmission power, which which is caused due to the overuse of the bandwidth, and the number of subscribers have increased. And since the number of subscribers have increased, the number of signals have increased, and hence there is more noise, more interference and fading. One of the biggest solutions, the emerging solutions right now, are the MIMO systems, or the multiple input multiple output systems. The advantages of MIMO systems are that they provide high data transmission rate by spatial multiplexing. Since there are more number of transmitters and receivers used, there is a wider system coverage and also link reliability by spatial diversity. But some of the problems that MIMO systems face are the fading problems, which causes inter-symbol interference, and also problems with the power and throughput. Inter-symbol interference is nothing but the symbols in a signal interacting with each other and not giving a well-defined output. Hence, the noise, we cannot differentiate between the noise and the actual signal. Now, inter-symbol interference can be taken care of by three different uh, schemes, that are equalization, diversity and channel coding. In my project, I'll be talking about equalizers, and mainly two equalizers, that are zero forcing equalizers and MMSE equalizers. Now, equalizers are nothing but recovery mechanisms. They can be linear filters or complex algorithms. Two of the linear filters are zero forcing equalizers and minimum mean square error equalizers. Now, when they are used along with successive interference cancellation, it is found that the performance is better. This is what I am going to discuss in my project today. We can see the coefficient matrix of zero forcing equalizers here, given by DZF. Now, zero forcing equalizer is nothing but a simple inverse filter which takes the impulse response of the received signal and inverses it, and then these two are multiplied to get an output. The problem with zero forcing equalizer is, since it is multiplying with its own inverse, there can be noise amplification. This noise amplification can distort the whole system, and hence zero forcing equalizer generally neglects the whole noise itself and cannot be used much in practicality. But it is found that zero forcing equalizers at high SNR regimes works almost as well as other equalizers. Now, the here we can see the SNR given by SNR input divided by the coefficient matrix transpose and the coefficient multiplication of the coefficient matrix transpose and the coefficient matrix inverse. Probability of error is also given. As we can see, SNR plays a great role, and hence amplification of noise can happen. Now, moving on to minimum mean square error equalizer. As the name suggests, it just minimizes the minimum mean square error between the transmitted signal and the received signal. This reduces the interference to a great amount. Here we can see that the coefficient matrix D is given by the inverse of B transpose and B plus N naught into I, where N naught is the noise. Now, SNR is given by this, and probability of error is given here, we can see that it is highly dependent on the SNR of the zero forcing equalizers. So in the end, it does depend on zero forcing equalization, but it's a little better because it minimizes the mean square error to a much greater extent compared to zero forcing, which can amplify noise. The minimization can occur recursively, and hence we can get a recursive algorithm which is more helpful. Now I'm going to talk about successive interference cancellation. This is a physical layer technique and it can provide significant throughput gain. What successive interference cancellation does is that it takes the highest power signals from the signal that we have already got, then it decodes the strongest signals, and subtracts it with the combined signal. Now, once you subtract it, we are assuming that the highest signal will reduce the error. Now, this is done recursively, successively to get better outputs, and in the end, it is found that it effectively does reduce the interference. Now, by using successive interference cancellation with the other equalizers, we found that the error rate reduces to a greater extent. But one problem with successive interference cancellation is that it might reduce the power of the total output, but sometimes it may not reduce the noise effectively. In these cases, the necessity of optimal ordering comes into picture. Optimal ordering is used so that it can find out the signals with the highest SNR, and those are used for successive interference cancellation instead of just the highest power signals. So thus low error probability is found. Now we can see that the power of the one of the first antenna is given here, and the power of the second antenna is given here. Now these two are re-estimated and we get a re-estimated signal T, which helps in successive interference cancellation. So what optimal ordering does is it will choose with the signal with high SNR. If the higher SNR signal is x2, then x2 is excluded and only x1 is considered in this condition. And if x1 is excluded, then x2 is found here. These are the re-estimated signals after the power exclusion of the other signal. Now in my project, I am going to talk about a MIMO system with 2 transmit antennas and 2 receive antennas. Also, I will be using BPSK modulation and also Rayleigh fading channel. The outputs, the signals at the receiver are given here as Y1 and Y2. The probability of error of BPSK is this, and since we are using a Rayleigh channel, the probability of BPSK is used along with the Rayleigh channel probability distribution function to get this probability of error. Now I am going to talk about the codes that I have used. Here we can see that this is nothing but the zero forcing SIC, that is successive interference cancellation, along with optimal ordering. In the project, I have also simulated normal ZF and normal MSE equalizers, but here I choose to talk about zero forcing equalizers with SIC and optimal ordering. First, we use the number of bits or symbols. It's generally taken a high amount, which is what is used practically, and then we come to the transmitter. Here at the transmitter, we randomly generate signals with equal probability of 0 and 1 is randomly generated with equal probability. Then BPSK modulation is done at the transmitter, and then we have the Rayleigh channel which is considered, and a wide Gaussian noise. Wide Gaussian noise is to increase the practicality of the whole system. Now this whole is this Rayleigh channel probability, PPSK probability and Gaussian noise are added and sent. This is the signal that is transmitted. Now at the receiver, since it's a zero forcing equalization, we find the inverse of the matrix. The inverse of the matrix is found here, and then we continue on to sorting. Now sorting is nothing but optimal ordering. So what it does is sorting based on the channel power on each dimensions is sorted. Now since the second spatial dimension is equalized first, the second channel will have higher power. So first, that is the higher power channel is taken, and then sorting is done. Once sorting is done, it is used with the zero forcing equalization, and we finally get the receiver hard decision coding, which will help us get the new received symbol. This received symbol would have the second spatial dimension effects removed from it. This is the after successive interference cancellation. This is what we get. Then we go on to simulate the bit error rate with respect to EB by N naught. Now here we have used successive interference cancellation only once, and hence we can assume that the values are not exactly right. Now comes this is the MMSE equalizer with SIC and optimal ordering. It is similar to the ZF optimal SIC with optimal ordering. The same thing happens. Firstly, the random zeros and ones are generated, then BPSK modulation is considered, then we consider Rayleigh channel and wide Gaussian noise. The signal that is sent is this. Now at the receiver end we have to find the inverse, but in this case there is a sigma 2i added to the matrix for minimum mean squared error. So this is the difference here that we can see, and it continues on to sorting. Now the equalization matrix is based on the channel power on each dimension. So what happens is, as I discussed before, the second spatial dimension is equalized first because it has high power. As you know how it works, a successive interference cancellation works this way, and then these are sorted. After sorting, equalization is enforced, and once equalization is enforced, we receive a new symbol here. After receiving the symbol, we are going to reshape the symbol to get a better output, and we go on to simulate the bit error rate and with respect to EB by N naught. Now these are the MATLAB codes as I have used. Now I will show you the graphs. Here we can see that the blue line is the MIMO with zero forcing, which is simulated in the other ones that I have already given, and codes that I've already given. We can see that ZF-SIC has better performance. Similarly, here we can see that MMSE SIC has the best performance. Now my conclusion is that BER is improved, ISI is removed at high SNR, similar performance, and there is similar performance between ZF and MMSE, but the limitations are due to the design consideration that I have taken. It may not be completely practical, and this is the end of my project. Thank you.